Okay, so today we are going to be looking at, get the cursor out of the way. So we are going to be looking at 7.2. 7.2 deals with what is called partial derivatives. And basically what that means and what we're going to be doing is we're going to be taking derivatives of multiple variable functions. Okay, so before we get into it, we're going to take a little bit of time to review some of the derivative rules. And that takes us back to chapter 2. So if we have the function f of x equals 3x squared plus 3, what I want to remind you of is that this 3 is a coefficient constant multiple, and this 3 is just a constant. Now, the reason I want to point that out is I want to look at and let's remember how we treated those values when we are taking derivatives. So if we're going to take the first derivative, then we've done it so often now we go straight to it. We may even forget what the rule is called, but we treat the coefficient constant multiple, meaning we just leave it there, times, and then of course we bring this 2 out front, x to the 2 minus 1, which is just 1. So what I want to remind you is that coefficient constant multiple, that number in front just gets brought down and will be multiplied times the derivative of the variable. And then of course the derivative of a constant is just 0. So we know that first derivative is 6x. Now, I'm being purposeful, and why we're going over that is because it gets a little bit, well, we'll one, be using it, but now we have multiple variables. So sometimes it can cause a little bit of difficulty for some. So now what we're going to do is we're going to look at the derivative of multiple variable functions, which, as I stated earlier, that's also known as partial derivatives. They mean the same thing, okay? All right, so the first thing that you're going to do is take the derivative, WRT, that means with respect to one variable. So we now have multiple variables, but when we take the derivative, we'll only be taking the derivative with respect to one of those variables, not both at the same time. So what that means is if I take it with respect to x, we took the derivative here with the variable x, so now we're going to also have a y in there. So what do we do with the y? So the other variables are treated as constant multiples or constants. So what that means is if we're taking the derivative with respect to x, then anywhere there's a y, we have to look at that y as a constant multiple like this 3, or just a constant like this 3. So that's where you have to be very careful and intentional as you're working these to keep that all straight. So let's look at an example. So let's start part A. We have the function, two variables, x, y, and we're given x to the 4th y cubed. So that's the function, two variables. So what does it look like when we take it with respect to one of the variables? So if you see the writing where there is a sub x, that means f of x. So what that means is we are taking the derivative with respect to x, okay? So we're going to take the derivative of this with respect to x. So what that means is the other variable is either a constant multiple or a constant. And since it's being multiplied times the x to the fourth, we'll look at this as a constant multiple. So we will not view that as 3y squared, because that's taking the derivative with respect to y. So we just treat it as a constant multiple, which means we just leave it alone. So what we'll do is we can take the derivative of this because it's with respect to x. So this would be 4x cubed. This is treated as a constant multiple, so we just leave it alone. So now we've taken the derivative of this function with respect to x. So let's look at that same function. And now let's take the derivative with respect to y. So now the y variable is what we'll take the derivative of. That means the other variable, so in this case, our x to the fourth, is our constant multiple, which means don't take the derivative of the x. Just leave it alone. So we'll leave this alone because it's like a constant multiple, just like that 3 up above here. We take the derivative of y cubed, which would be 3y squared. And then, of course, I'm going to clean it up a little bit because we always put the numerical value in front. So I would rewrite this as 3x to the fourth y squared. So here is the function, the first derivative with respect to x, and then the first derivative with respect to y is this right here. Now, I always start out with a pretty simple example. So we've got to look at other scenarios that can occur with a little bit more difficult functions involved. All right. The next example, part A, multivariable function f of x, y is equal to x squared plus y squared plus 2xy minus 3x squared y squared plus 9. So what we're going to do first is we are going to take the derivative with respect to x. So what that means is the other variable will either be a constant or a constant multiple. And I'm going to go ahead and for right now and continue to circle those just to be helpful. So notice this one stands alone. So we'll treat that as just a constant. This y and this y squared is being multiplied times something else. So those will be a constant multiple variable. All right. So I start here. We know that's 2x. This is treated as a constant. So the derivative of a constant is 0. Then we have plus 2 is a constant multiple. The derivative of x is just 1. And then the y is also a constant multiple. So we just write y. Minus, we have the 3. The derivative of x squared is 2x. And the y squared is treated as a constant multiple, so it just stays y squared. And then, of course, the derivative of a constant is 0. So that's showing every single step. So hopefully you'll get to a point where you won't necessarily have to show all this work. But definitely in the introduction, I want you to see where everything comes from. So now I'm just going to clean it up. So we now have the first derivative with respect to x. So now I'm going to rewrite that same function. And now we're going to look at the derivative with respect to y. So now y is what we're taking the derivative of. So that means every other variable, so in this case, your x's, so this will be treated as a constant. This x and this x squared will be treated as constant multiple variable. So the derivative of a constant that stands alone is 0. And we know this is 2y. That's a constant multiple. That's a constant multiple. The derivative of y is 1. Minus 3 is a constant multiple. X squared is a constant multiple. And then the derivative of y squared is 2y. And then, of course, 9 is a constant, so it's 0. So in cleaning it up, we would have 2y plus 2x minus 3, nope, how about 6? 3 times 2 is 6, so we have 6 x squared y. So that is a 6, so be careful of that. I about neglected to multiply that 3 times 2, okay? All right, so moving on, because now we want to get back to and apply what we've been learning with functions that have logs and exponents. All right, so let me write this first one and then let's see. Okay, so we're going to do an example, part A. And we have f of xy equals e to the 3x squared natural log of y. Okay, so before we take the derivatives, I want to take you back to chapter 4 in the formula sheet that you got to use, because you've got to remember how to take the derivative when you have a natural log and when you have e raised to some power, because we're dealing with both of those here. So a natural log, just look at what follows the natural log, and in the numerator, it's the derivative of that over that, whatever the natural log is. And then if you're doing or looking at the derivative of e raised to something, then remember, just rewrite it and then take the derivative of the exponent. So that these are going to come into play as we take these derivatives. All right, so the first we're going to do is with respect to x. So that means anything with the y is going to be considered a constant or a constant multiple. And since this is being multiplied times this, it's going to be a constant multiple, which means just leave it alone. So now what we have to do is we have to take the derivative of this, which is why I showed you that formula sheet, because what we do first is we just rewrite it, leave it alone, times, now we take the derivative of 3x squared, which is 2 times 3, 6, x to the 2 minus 1 is 1. So we get 6x times, we treat this as a constant multiple. So we just rewrite it as the natural log of y. So if I'm going to clean that up, then I'm going to put 6x in the front. So we have 6x e to the 3x squared natural log of y. So this is the first derivative with respect to x. So now we're going to take that same original function and now we are going to take the first derivative with respect to y. So that means this that has the other variable x, treat it as, and in this case, a constant multiple. All right. So if this is treated as a constant multiple, we just leave it alone, times, and then we're going to take the derivative of this. Now, again, that's why I showed you that formula sheet from chapter 4, because here's my function, which is just y. So the numerator is the derivative of y, which would just be 1. And then the denominator is just that function, which in this case is y. So you can leave it as that, or you could rewrite it as e to the 3x squared over y. These two mean the same thing. I would take either. Just pay attention into WebAssign. I'm not sure which they prefer, or even if they care. They may take both of them. All right. Moving on. All right, so that was logs and exponents. Now we're going to look at how to handle a partial function to a power. So here's an example of what I'm talking about here. So if we have the function in parentheses xy squared plus 2 raised to the third power. Now, the reason this is a function to a power is because this exponent is on the outside of the parentheses. So if you recall, we bring this down, 3 goes in front of it, leave this alone, 3 minus 1 is 2, and then, and this is the part most students forget to do, and that is don't forget to then finish it by taking the derivative of the junk, what is inside the parentheses. So that's when you will have to pay attention. Am I taking the derivative with respect to x or with respect to y? So we're going to start out with respect to x. So we bring this 3 down, leave what's inside the parentheses the same. 3 minus 1 is 2. And then this last part is what students forget to do. And that is just look at what's inside and take the derivative with respect to x. So this y squared will be treated as a constant multiple. So, of course, the derivative of x is 1, y squared is a constant multiple, plus the derivative of 2 is just 0. So we actually have y squared plus 0, which is just y squared. So in cleaning it up, we have this 3. I'm going to simplify this to y squared and bring it out front. And then, of course, what's inside the parentheses, we leave alone. And there's our first derivative with respect to x. So we're going to do part B. So I'm going to rewrite the original function. And you guessed it, now we're going to do it with respect to y. So again, bring the 3 down, leave what's in the parentheses alone. 3 minus 1 is 2. Now we're going to multiply this, and now I need to take the derivative of the junk. Okay, but now it's with respect to y. So in that case, then this x is my constant multiple. So we leave it alone. The derivative of y squared is 2y, and of course the derivative of 2 is 0. So this is 2xy. So in cleaning it up, I'm going to multiply 3 times 2, which is 6. Then we have this x, this y, and then xy squared plus 2 squared. Whoops. I like to keep my colors the same. I grabbed my pink highlighter and I wanted my green one. All right, so that's partial function to a power. All right. Now, and this one sometimes causes people problem. And why does this next example cause problems? Because students did not take the time to learn the rule and how to do it back when we had done this type of derivative earlier. And this is the partial of a quotient All right, quotient means you have a numerator and a denominator. So remember that is low D high minus high D low all over low squared. So the denominator times the derivative of the numerator minus the numerator times the derivative of the denominator all over the denominator squared. Okay. All right. So let's see if yeah. Okay. Here's the example. We have the function g of xy equals xy over x cubed plus y cubed. All right, so we have a numerator and denominator. So now we're going to take the derivative with respect to x. So we're going to follow this. And when we do it with respect to x, when we take the derivative, we know that these are constant or constant multiples. All right, so we start out low, so we just leave that alone, times the derivative of high. And so the derivative of x is 1, and then y is treated as a constant multiple, minus high times the derivative of low. Y cubed is your constant in this. Oh, yeah, I'm still here. Sorry. So we have 3x squared plus 0, because that's a constant, all over low squared. So now I'm just going to clean it up a little bit. This y I'm going to put out front. Minus here, this is 0, so we have 3x cubed y. And then please do not say that this is x to the 6th plus y to the 6th. That means with this squared on the outside, it means you would take x cubed plus y cubed times x cubed plus y cubed times x cubed plus y cubed. We're not going to do all that multiplication. We're just going to leave it alone as x cubed plus y cubed squared. Now, we're going to now do that same function, but now we're going to do it with respect to y. And I'm going to have to get another piece of paper because I don't think I can get it at the bottom of that. So this is part B. So that function, the original function, was xy over x cubed plus y cubed. But now we're going to find the derivative with respect to y. So what that means is now the x's are my constant or constant multiples. All right, so again, low times the derivative of high. X is a constant multiple. Derivative of y is 1 minus high times the derivative of low. This is a constant, so that's 0, and this would be 3y squared. All over low squared. So in cleaning that up, I'm going to put the x out front. And then that's 0, so I have 3xy cubed. And then I'm just going to leave that denominator alone. I don't want to get into multiplying that. And I think on the previous, I'd said you'd multiply it times 3 times. It's just squared. You'd do it twice. I may have said that wrong. So it doesn't affect the problem, so it's all good. All right. Now we're going to look at another example that's a partial of a log. We looked at log and exponents. This is just going to be a partial of a log. And the reason is because we've not done another example like this, and you're probably going to encounter something similar in WebAssign. So here's the function, and then it's going to say find f of something, and it's going to give you an ordered pair. All right, so for all the examples I've done up to now, we have found the derivative with respect to x and with respect to y. But in this particular problem, there is no reason to take the time to find the derivative with respect to x, because this one's just saying, hey, all you have to do is find the derivative with respect to y. Once you do that, then plug in that ordered pair. Now, here's where you need to be careful. Students will jump right in and start trying to take the derivative of this with respect to y, but because of this square root, you have to pause. So first, what you want to do is you want to rewrite that function with the square root as an exponent. So I'm going to rewrite it as the natural log of x plus y to the 1/2. And then the next thing that you have to remember is those natural log rules, and those are on that chapter 4 formula sheet as well. And that tells me, even before I start taking the derivative, that we can bring this, let me show you where this is. It's right here. So the exponent just comes out front. So we're going to bring 1/2 the natural log of x plus y. Now, some of y'all might be thinking, oh, I have to do 1/2 minus 1. No, we're not taking the derivative yet. All we're doing is rewriting it with those natural log rules. Okay, so we haven't taken the derivative. That rule tells me I can bring this exponent and put it out front, and then it goes away right here. So be careful. Are you using a natural log rule, or are you actually taking the derivative? So you have to be careful of that. All right, so now we're finally going to get to the point where we want to take the derivative with respect to y. So now I'm going to take the derivative with respect to y. So I'm going to look at this and I'm going to remind myself then this is treated as a constant. All right, so this is a constant multiple. So 1/2 times, now the natural log, so that tells me I'm going to have a numerator and a denominator. So the numerator is the derivative of this with respect to y. So this would be 0 plus 1. And then we just rewrite that in the denominator. And now cleaning it up, this is on top. So it's 1 times 1, which is 1. And then I have 2 times x plus y. So what we did first was we found the derivative. Oh, I grabbed pink. I should have grabbed. That's going to bug me. Sorry. It's getting green, even though it really doesn't matter, but it does to me because it bugs me. All right. So we've done the first part, but now we're going to substitute in. So we have the derivative, and we're going to substitute 5 in. Anywhere there's an x, and -1 anywhere there's a y. So I'd have 1 over 2 times 5 minus 1. So 1 over 2 times 4. So I get 1/8. If it has you enter it as a fraction, or that converted to a decimal is 0.125. Just pay attention to the way WebAssign wants you to enter it. Okay. All right. Now we're going to look at what is called second order partials, which just means we're taking the second derivative. All right, so we've been taking the first derivative. Now we're going to look at taking the second derivative. All right, so let's look at an example because there's lots of different things that are going to be happening here. All right, so we have the function, whoops, didn't mean to put an equal there, f of xy is x to the fourth plus 3x squared y squared plus x cubed y plus y to the fourth. All right, so we're first going to take the derivative with respect to x. This is the first derivative, okay? So what that means is that my y's are constant multiples or constants. So I'm going to go through this pretty quickly. Hopefully you're kind of getting the hang of this. So this would give us 4x cubed plus 3 times 2x times y squared plus 3x squared times y plus 0. So I'm just going to clean that up. 4x cubed plus 6xy squared plus 3x squared y. All right, so here's the first derivative right here. All right, so now we're going to get into the second derivative. All right, so one question that could be asked is they could say, all right, f of x, x. So what that means is take the second derivative with respect to x. This first x is the first derivative with respect to x. Now use that function and take the second derivative with respect to x. So we're going to look here in this one. X, you're going to take the derivative, so the y squareds and this y are your constant multiple. So we would have 12x squared plus 6 times 1 times y squared plus 3 times 2x times y. So in cleaning that up, we get 12x squared plus 6y squared plus 6xy. So here is your second derivative. What you can also do, and you may be asked to do, here we go, f's of xy. So that means here's your first derivative with respect to x. Now take that function and take its derivative with respect to y. So now when we look at this, your x's variables are going to be your constant or constant multiples. So this is a constant now with respect to y, so that would be 0 plus 6 times x times 2y plus 3 times x squared times 1. And then, of course, when we clean that up, we get 12xy plus 3x squared. All right. Okay. Now, part B. So I'm now going to, again, look at that original function, f of x, y equals x to the fourth plus 3x squared y squared plus x cubed y plus y to the fourth. And I would assume you can guess we're going to do the first derivative now with respect to y. So my x's now are either constant or constant multiples. Let me move this up. All right, so constant 0 plus 3x squared times 2y plus x cubed times 1 plus 4 y cubed. So in cleaning that up, we get 6x squared y plus x cubed plus 4y cubed. So this is the first derivative with respect to y. So now we're going to look at second derivatives. So here's my first derivative with respect to y. So now in a second derivative, we're going to look at this derivative function and take its derivative with respect to y. So that means your x's are either constant multiples or constants. So we would get 6x squared times 1 plus, this is a constant, which would be 0, plus this would be 4 times 3y squared. So f sub y gives us 6x squared plus 12y squared. And then we're also going to find f sub y. So looking at this first derivative, but now what we're going to do is the second derivative is going to be with respect to x. So that means your y's are your constant multiples or your constant. So we would get 6 times 2x times y plus 3x squared plus, this is a constant, so that would be 0. So f sub yx equals 12xy plus 3x squared. Now, we've been doing a lot of work. You may not notice this, but I want to draw your attention to f sub xy and f sub yx. 12xy plus 3x squared. What do you know? They gave us the same thing. All right, we're going to look at an application problem, and then we will be done with this section. All right, so let's suppose we're looking at cells of a TV, and you're given the cells function, multivariable, is, 200 minus 0.1x plus 0.2y squared. So this cells function was given to us. I didn't not have to create that. And x represents the price of the TV. And y represents the amount spent on ads. All right, so let's suppose part A said, find the marginal sales functions. All right, first off, you're going to have to remember what this word means to do. When you see the word marginal, you know it's talking about, hey, take the derivative. Now also notice it says take the derivative of the cells functions, or find the marginal cells functions. Multiple, we have multivariables, so we need to find it with respect to x and with respect to y. So we're going to take the cells function and we're going to find the first derivative with respect to x. So with respect to x, that means that anything that's a y is a constant or a constant multiple. So this, the derivative of this 200 is a constant, so that's 0, minus the derivative of this would just be 0.1, and then this would be another constant. So with respect to x, we just get negative 0.1. Now we're going to find the marginal cells function with respect to y. So I'm going to come back up here, and so my x's are my constant, so this would be a constant, This would be a constant, so we would get 0 minus 0 plus, I'm going to take 2 times 0.2, which is 0.4. Y to the 2 minus 1 is 1. So we get 0.4 Y. So there are your marginal sales functions. All right. Part B, find and interpret S of X 500, 10,000. So remember, this is the price of the TV. This is the amount spent on ads. Okay. So S of X, so that means I'm going to take this function right here, S of X, and anywhere there's an X, I will put 500, and anywhere there's a Y, I'm going to put 10,000. Well, I look at this and I'm like, there isn't an X, there isn't a Y. So in essence, we don't have to substitute anything in. It's just going to be negative 0.1. Nothing to substitute in. Now, the interpret is what you may have forgotten how to do. Now, because of this is a negative, that means that, and in this case, we're talking about sales. So sales decrease by 0.1. Now, I don't put by negative 0.1. This word decrease is taking care of that negative. For every dollar increase in price. So we're not going to increase the price anymore, right? Because sales will start decreasing. All right, so C, find and interpret SOY at 500, 10,000. And so when you're looking at it with respect to Y, we have 0.4. We don't have any X's to substitute in the 500, so we just substitute in the 10,000, which 0.4 times 10,000 is 4,000. And notice it's a positive. So in this case, sales increase by 4,000 for each additional dollar amount spent on ads. Now, notice how here it says for every dollar increase in price. Now, why did I put that? Because this is X, and X is your price of the TV. So for every dollar increase in price, your sales are going to decrease. Down here, we said for each additional dollar spent on ads. Why? Because this is it with respect to Y. So sales will increase 4,000 for each additional dollar amount spent on ads. All right, so that should do it for 7.2.